Namaskar. In last session we were discussing about the power measurement for a 3-phase balanced system. Today we will start our discussion with the understanding about the unbalanced 3-phase system, and then we will also discuss how to measure the power in case of unbalanced 3-phase system. So, let us start our discussion of today's lecture. First, let us understand what is unbalanced system. So, unbalanced system is caused by two possible situations. One is that the source voltage are not equal in magnitude and or differ in phase by angle that are unequal. That means, for a balanced system we generally know that the phases are equally apart, equally distant with the respect to each other, that is 120 degree apart from each other. But in case of unbalanced system, the phases will not be exactly 120 degree apart, there would be some phase difference. So, in that case we will say that the system is unbalanced. Second case might be the case of unbalanced load, where the load impedances are unequal. So, these are the two possible conditions under which we say that the 3-phase system is unbalanced. So, therefore, we can say that unbalanced system is due to unbalanced voltage sources or unbalanced load. Now, to simplify the analysis related to unbalanced system, in this particular session we will assume that the source is balanced, means the voltages magnitude as well as angle are as per the balanced voltage source, but the load is unbalanced. It means that the load impedances, that is Z A, Z B, Z C are not same. So, in that case, for the unbalanced 3-phase system, the various electrical parameters can be calculated by direct application of either mesh or nodal analysis. So, in the figure which we just saw in this slide, this is an example of unbalanced 3-phase star star, or you can also say Y system that consists of balanced source. So, balanced source is behind the particular nodes which we are seeing. So, we are not showing that in the figure, but since our objective is to analyze the circuit by assuming unbalanced load. So, we are showing only the unbalanced load in the figure. So, we will see only the unbalanced load as we saw in the previous figure. Here in case of unbalanced load, Z A, Z B, Z C are the phase impedances which are not equal. Now, when we calculate the line current, we calculate the line current with the help of Ohm's law. So, I A, that is the line current for line A, then for line B and C is I B and I C. So, we will calculate the value of line current. So, I A will be V A N divided by Z A. V A N is nothing but the voltage across the Z A impedance divided by the impedance Z A. So, you will get line current I A as V A N by Z A. Similarly, I B will be V B N by Z B and I C will be V C N by Z C. So, A N, V A N, V B N, V C N are the voltages across the individual impedances of the phases. Now, this set of unbalanced line current produce current in the neutral wire, because the total sum of line currents, that is I A plus I B plus I C, will not be 0, which we saw in case of balanced system. So, in that case, if we apply KCL at node N, we get the value of neutral current, that is I N equal to minus of I A plus I B plus I C. Now, in case where we see the 3 wire system, that means the neutral line is absent, we can still find the line current I A, I B, I C using mesh analysis, but in those cases when the neutral line is absent, at node n KCL will still hold, that means I A plus I B plus I C will be 0. Now, this we have analyzed with the help of star star or Y Y connected system. Same we can do for the unbalanced delta Y, Y delta or delta delta 3 phase 3 wire systems. So, as we mentioned earlier, the long distance power transmission conductors in multiples of 3, that is we have 3 phase 3 wire system. So, are used. So, in that case the earth itself will act as a neutral conductor. So, we do not lay the neutral conductor along the long transmission line, we use earth as a neutral conductor. Now, to calculate the power in an unbalanced 3 phase system, what we require? We require that we find the power in each phase using the equation which we have seen earlier also. So, like real power in phase we can write as V p I p into cos theta. V p is the phase voltage, I p is phase current multiplied by cos theta. Similarly, the reactive power per phase can be written as V p into I p sin theta. The magnitude of apparent power you can write as V p into I p, and the complex power we can write as P per phase plus j q p, or we can write V p into I p conjugate. So, these are something which we have already discussed. So, we will straight away go to the calculation of total power in case of unbalanced 3 phase system. So, here since the system is unbalanced, the total power is not simply the 3 times of the power in one phase. So, we cannot say that the total power P will be 3 times of P p or 3 times of Q p, if we are considering real and reactive power of the complete 3 phase system. So, in that case how we will calculate the total power? In that case we will find out the total power as the sum of powers in 3 phases. So, in that case we will write P, that is total power for the 3 phase system, will be P a plus P b plus P c. Now, let us see how we will measure this power, because we have found the condition that under unbalanced condition we will get the value of power P as a sum of individual powers in each phase. How will calculate or how will measure this power? We will use different techniques for 3 phase power measurement. Let us discuss the techniques which we will use for the measurement of 3 phase power. So, if we use the wattmeter in case of balanced system, single wattmeter can be used to measure the average power in a 3 phase system, because when we have the system completely balanced, the power in each phase will be equal. So, if we measure power for one single phase, the total power will be 3 times of the reading of one wattmeter. Now, if the system is unbalanced, in that case the single wattmeter method cannot be utilized. In that case we need either 2 or 3 single phase wattmeters to find out the total power in case of unbalanced 3 phase system. Let us first try to understand how we will use 3 wattmeter method for power measurement. We will use the wattmeters connected in each phase of the line. So, how we will connect? We will connect the current coil in series and potential coil in parallel. So, parallel means the 0 is neutral, or you can consider any line through which we are able to find out the difference, potential difference between A and O. So, VAO will be the voltage which will be given by the potential coil, and we will get the total power, that is W1 from the meter W1. Similarly, for W2 and W3 meters, we will connect them to individual phases, that is B and C, and the potential coil, that is voltage coil, will be connected between phases and the reference node. So, we are considering reference node as O in this particular arrangement. Now, we need to find out how we will calculate the total power in case of 3 phase load, which may be connected as Y or delta, or it can be either balanced or unbalanced. So, now let us see how we will find the value of the total power being consumed by this load with the help of the reading which we get from these 3 watt meters. Now, this 3 watt meter method is well suited for power measurement in a 3 phase system, where power factor is constantly changing. So, the total average power in the case of 3 watt meter method will be the algebraic sum of 3 watt meter readings. So, that is P1, P2, Pt, P3, which we get is the power corresponding to the reading of W1, W2 and W3. Now, we have taken the reading with reference to common point O. So, we have selected it arbitrarily, but generally what happens in case of Y connected, the O will be nothing but the neutral point. So, that the voltage which you see across the potential coil will be the phase voltage. Now, if the load is delta connected, in that case the neutral point will be absent. So, in that case the reference point O can be connected to any phase. So, we can connect to either A, B or C if the load is delta connected. So, for example, if point O is connected to the phase B, that is point B, the voltage coil in the wattmeter W2 will read 0. So, therefore, the reading which we get from wattmeter W2 will be 0. That means that in this case the wattmeter W2 is not necessary to be connected. We can use only 2 watt meter for getting the power consumption details. So, we will also see that how 2 watt meter is sufficient to measure the total power. So, now this is the arrangement which you will see in case of 2 watt meter method, when you are asked to find out the total power consumed by the load. Here again the load is 3 phase, it can be star or delta connected, or it can be balanced or unbalanced. In this case, if you see the arrangement of watt meters, the current coil is connected in series with the phase A and phase C, and the potential coil is connected between 2 phases. So, for W1 the potential coil is connected between A and B, and for W2 the potential coil is connected between C and B. So, the 2 watt method is most commonly used method for 3 phase power measurement. 2 watt meters must be properly connected, as we see in this figure, for to any 2 phases which we have seen. And now notice that the current coil of each watt meter measures the line current. So, because it is connected in the line, while the respective potential coil, or we also say voltage coil, is connected between 2 lines. That means you will get the line voltage. Now, You also notice that the plus minus terminal of the voltage coil is connected to the line to which the corresponding current coil is connected. So, if you see the direction of the wattmeter connection, you will connect potential coil from where the current coil is connected. Now, although the individual wattmeters no longer read power taken by any particular phase, because these are the voltage which is coming across the potential coil is not the per phase voltage. So, in that case the individual wattmeters will not give you the reading of power consumed per phase or in a particular phase where it is connected, but the algebraic sum of two wattmeters will give us the reading which will be equal to total average power absorbed by the load, and this is regardless of whether the load is Y or delta connected or whether it is balanced or unbalanced. So, the total power will be equal to the algebraic sum of two wattmeter readings. Now, let us understand how we can justify the total power consumed is equal to the sum of the two wattmeter readings. For simplicity, we will take the two wattmeter method for a balanced three phase system, so that we can stabilize the relationship of the total power consumption versus the individual wattmeter reading. So, we will justify that the total power consumption is nothing but algebraic sum of two wattmeter readings. So, for that let us consider this particular circuit arrangement. In this you will see the voltage difference between phase and B is VAB, between phase B and C is VCB. VCB is written because the potential coil is connected from C to B. So, we will consider the C as plus point and B as minus. So, VCB will be the potential across the potential coil, because we consider B as a reference point for the connection of the wattmeter coils. Now, IB is the current which is flowing in B phase, IA in A phase and IC in C phase. So, these IA, IB, IC are also the line currents. Now, for simplicity we have assumed that the load is balanced. So, we will say the impedance of the load is ZY in all three phases. Now, the objective for this particular study is that we will apply 2 wattmeter method to find the average power absorbed by the load. Now, since we have considered the Y connected load and we assume the source is in ABC sequence. So, in that case the ZY, if you convert it into phasor, it will be magnitude with some angle theta. So, we assume that the load impedance will cause the voltage coil lead its current coil by theta, because this is the load which is applied. So, in that case what we can say that the power factor is cos theta. Also, if we recall what we discussed in case of balanced star star or YY connected network, we saw that the line voltage leads the corresponding phase voltage by 30 degree. So, in that case what we can write that the total phase difference between phase current IA and the line voltage VAB will be theta plus 30 degree. This is we have got when we take the reference as a phase voltage. So, your line voltage will be leading by 30 degree and theta is coming because of the load impedance. So, the total phase difference now you are getting between phase current, or you can also say line current, and line voltage VAB equal to theta plus 30 degree. So, in that case the average power which wattmeter W1 will read is real of VAB into IA conjugate. So, when you put the value of VAB and IA, you can simply say that the real component of VAB into IA conjugate will be VAB IA into cos theta plus 30 degree, or you can write VAB is nothing but the line voltage VL and IA is nothing but line current, that is IL. So, P1, the reading which you will get from wattmeter W1 will be the value of VL IL cos theta plus 30 degree. Similarly, if you see the reading of second wattmeter, so the value of P2, that is the reading of second wattmeter, can be written as real of VCB into IC conjugate. So, what you can write VCB into IC into cos theta minus 30 degree. So, now what you can write in terms of line voltage and line current, you can write P2 will give you the value of VL into IL cos theta minus 30 degree. Now, to find out the value of P1 plus P2, we will use the following trigonometric identities, that is cos A plus B is nothing but cos A cos B minus sin A sin B, and cos A minus B is nothing but cos A cos B plus sin A sin B. So, we will use these two formulas to find out the total value of power, that is P1 plus P2. So, if you rearrange the values, that is P1 plus P2, if you write VL into IL cos theta plus 30 plus cos theta minus 30. Now, these two you will expand with the help of trigonometric identity which we just saw. So, we will write cos theta plus 30 will be cos theta into cos 30 minus sin theta into sin 30, cos theta minus 30 will become cos theta into cos 30 plus sin theta into sin 30. Now, if you further simplify, you will get the value of P1 plus P2 as root 3 times VL into IL cos theta. So, from the above it can be observed that the sum of the wattmeter readings in the 2 wattmeter method will give the total average power, because if you remember we discussed that the total power in a 3 phase system, the total power consumed by the load will be root 3 times of VL IL cos theta. So, this is what we get from the 2 wattmeter algebraic sum. So, this justifies that the total sum of 2 wattmeters will give us the total real power consumed by the 3 phase load. Now, let us go further and try to find out the value of P1 minus P2. So, we will use again the trigonometric identities and try to find out the value of P1 minus P2. So, when you put the values, expand it, and when you simplify, you get the value of P1 minus P2 as minus of VL IL sin theta. So, that means P2 minus P1 will be VL IL sin theta. Now, if you multiply by root 3 on the both sides, the value which you get on the right side is root 3 times VL IL sin theta, that is nothing but the total reactive power consumed by the load, that is 3 phase load. So, what you can write? You can write the total reactive power consumed by the 3 phase load is equal to root 3 times of P2 minus P1. So, the apparent power you can now write, that is total apparent power ST is nothing but under root of PT square plus QT square, or you can write the wattmeter reading W1 plus W2 square plus root 3 times of W2 minus W1 square. So, this will give you the total apparent power for the load. Now, for the power factor, what you can write? Tan theta is nothing but QT by PT, and if you put the values of QT and PT, what you can write? QT will be root 3 times of P2 minus P1 and PT is P1 plus P2. So, with this you can easily find out the power factor also. So, when you get the value of tan theta, the power factor will be the value of cos theta. So, what you can say that the 2 wattmeter method is not only providing the total real power, but also the reactive power and the power factor. Now, from the above equation you can observe that the total load will be resistive when P 2 equal to P 1. When P 2 is greater than P 1, the load will be inductive because tan theta will be positive, and P 2, if P 2 is less than P 1, the load will be capacitive because your value of tan theta will be negative. Now, let us take couple of examples to understand what we have discussed till now. Let us see if we have unbalanced star connected load as shown in the figure is connected to balanced voltage of 100 volt and the phase sequence is ACB. We need to calculate the line currents and the neutral current for this particular arrangement, where the ZA, ZB and ZC are given as ZA equal to 15 ohm, ZB is equal to 10 plus J5, ZC is equal to 6 minus J8 ohm. So, if you see this particular star connected load, ZA, ZB, ZC are not equal. So, that means we have to solve for line current separately because the line currents are not equal and the system is unbalanced. So, what we will calculate for IA, the value of line current will be the voltage across the load, that is 100 angle 0 divided by 15, that is the value of impedance ZA. We get the value of line current IA, that is 6.67 angle 0 degree. Similarly, for IB we write 100 angle 120 degree. Here you have to be very careful because here the sequence is ACB, not ABC. So, in that case your voltage, that is VB, and which you see in the circuit will be 100 angle 120 degree, and then you divide by ZB, you get the value of IB. Similarly, IC you will get 100 angle minus 120 degree divided by ZC, you get the value of current IC. To get the value of neutral current, IN will be nothing but equal to minus of IA plus IB plus IC. So, when you sum up, you will get the value of neutral current as 10.06 angle 178.4 degree ampere. Now, let us take another example. So, in the previous problem what we saw, we will use 3 watt meter method, where the watt meters are connected to individual phases to measure the total power absorbed by the unbalanced Y connected load. What we need to find out? We need to find out the watt meter readings and the total power absorbed. So, in this case we know VAN is 100 angle 0 degree, VBN is 100 angle 120, VCN is 100 angle minus 120 degree. IA, IB, IC we have calculated in the previous example. So, the watt meter readings you can simply find out. The value of P1 will be real component of VAN into IA conjugate. So, when you find the value, it will become VAN IA cos theta VAN minus theta IA. Now, if you put the values of all the parameters, you will get the value of P1 as 667 watt. Similarly, for P2 it will be the real part of VBN into IB conjugate, which you get VBN into IB cos theta VBN minus theta IB. So, now theta VBN will be 120, theta IB you have got 93.44 degree. So, the value of P2 you will get as 800 watt. Similarly, for P3 you just put the calculate the value of real of VCN into IC conjugate, which is nothing but VCN into IC cos of theta VCN minus theta IC. If you put the value, you will get the value of P3 as 600 watt. Now, the total power absorbed by the load will be PT equal to P1 plus P2 plus P3. So, you get 2067 watt. Now, if you want to cross verify whether you have arrived at the correct value of P, what we can do? We can simply find the power absorbed by the individual resistors, because the circuit contains 3 resistors and real power will only be absorbed by the resistors. So, 15, 6 ohm and 10 ohm are the resistors. So, what we can do? We can just calculate the value of I square R for each and individual phases, and when we sum up, we get the value of total power absorbed by the load is equal to 2067 watt. So, this says that we have arrived at the correct value of real power. Now, let us see quickly the third method also, third example also, where we need to use the 2 wattmeter method to find the value of per phase average power, per phase reactive power and the power factor. P1 and P2 is given and the line voltage is 220 volt. Since P1 and P2 is given, total power average power you will get as P1 plus P2 is equal to 3660 watt. So, you can say that per phase average would be 1/3 of the total power. So, you will get 120 watt. Now, total reactive power you will get equal to root 3 into P2 minus P1. So, you will get 935.5 var. So, per phase reactive power you will get as 1/3 of total power, that is 311.77 var. The power angle you can quickly calculate, theta is equal to tan inverse of QT upon PT. QT you calculated as 935.3 and PT you calculate 3660 watt. So, you just put the value and simplify, you get theta as 14.33 degree. So, power factor in this particular case will be 0.9689 lagging. Since P2 is greater than Q1, it means that power factor is lagging. So, with this we can close our today's session, in which we discussed about the unbalanced 3-phase system. In next week we will start our the topic related to state variable analysis. Thank you.